Kia ora and welcome to video 4, question 4 of the 2024 School Calc exam. The first question here is complex numbers. It's a pretty standard question based on NCA level 3. The second question here involves complex numbers and a little bit of trig identity proofs, pretty straightforward. And then this third question is it's a little bit of a humdinger. The first part is pretty much straight conics. You have to understand your definitions of conics, well, the definition of a parabola to be able to solve it. And then the second part here is more coordinate geometry slash conics, but set in a related rates context, which makes the problem have that extra layer of difficulty, and in my opinion was the hardest question in the 2024 School Calc exam. So probably tested the top scholar and the students aiming for outstanding. Alrighty, question 4a. So first up, you need to be able to understand what this notation here is saying. The argument of a complex number is its angle anti-clockwise from the positive real axis. So we need to sketch complex numbers that are in between 60 degrees and minus 60 degrees. Something to be wary of here is that if you have a 60 degree or pi over 3 angle there inside a triangle, then this relates to a special triangle where that's half of an equilateral, that is 2, that's root 3, and that's 1. So when we sketch the locus down the bottom here on the grid, we need to make sure that the line has a slope of root 3 over 1. This question isn't very helpful. The grid here is not very helpful because it's not square, which means that when we graph the circle later, it's going to look like an ellipse. Not helpful. But let's just get this argument of z in between minus pi over 3 and pi over 3 sorted. If we go out 1 up root 3, or out 2 up 2 lots of root 3, we're going to be about here. If I draw that line, oh, that's close enough. It doesn't look like a 60 degree angle again because the grid's not square. If I do the same thing in the opposite direction, that's close enough. So we get all of the complex numbers that are inside here will satisfy the first condition. The argument is between 60 degrees and minus 60 degrees. I'm not going to shade in yet because it's going to get a bit messy if I do. The second one, z plus its conjugate is less than or equal to 4. If we just chuck that in, some basic algebra into that, x plus iy plus x minus iy is less than or equal to 4. The imaginary parts cancel and we get 2x less than or equal to 4, or x is less than or equal to 2. So any complex number where the real part is less than or equal to 2, the imaginary part can be anything because the y value is not restricted in that case. So that's just a vertical line going through 2. Again, we would shade over here to say that that is the answer to the problem. However, I'm not going to shade yet. We're inside the triangle though. And then the last one, either you think of it algebraically or geometrically. Geometrically, the modulus of z is greater than or equal to 2, means that the complex number must be at least 2 away from the origin. So we would think about what a circle would look like. It's got to be outside of the circle, and as I was saying earlier, if I sketch this, it doesn't quite look like a circle because the grid's not perfectly square. If we do this algebraically, then we've got the modulus of x plus iy is greater than or equal to 2. The modulus of a complex number is the real part squared plus the imaginary part squared, square rooted. That's Pythagoras. Notice that the I doesn't go with that when you're finding the modulus of a complex number. Squaring both sides, we don't have to worry about the inequality flipping because you're multiplying both sides by a positive quantity. The square root is a positive and 2 is obviously positive, so we get that. Now that's an equation of a circle where the radius is 2 or more. So we're shading outside of the circle here, and I shouldn't have drawn a dashed line because dashed lines in the Cartesian plane represent not equal to. So we would be outside of this range here. But again, the shading out is a little bit messy, so let's just get rid of that and focus in on the region of which the answer occurs is, the answers, because there's more than one. Z has to be inside that little piece there or inside that little piece there. Now, we could use integration to find the area of this region. However, you don't need to. Because we know the slope of the two lines that I drew right at the start, this equation is y equals square root 3 of x. And this one here is y equals minus square root 3 of x. We know that the angle in there is 120 degrees. So we've actually got a triangle where we can either use half a b sine c. It's actually easier in this question to just use half base times height, and we don't need that angle. Oopsies. If we just look at half base times height, sideways the height is 2 and the base is this length here is 2 root 3 and this length here is 2 root 3, so 4 root 3. So area of a triangle is half times base times height, which equals 4 root 3. And then of course we need to remove this little sector, and that's where the 120 degree angle is used, because 120 is a third of a circle, and the radius of that circle is 2. So area of the sector is a third of pi times radius squared. And that there is 4 pi over 3. So therefore the area of the locus which satisfies the 3 conditions, in other words z can be anywhere in here or anywhere in there, the area of that region is the triangle 4 root 3 minus the sector 4 pi over 3. Alrighty. Part B is an example of a question where complex number basics is needed, but also a bit of trig identity work. And a lot of students don't do trig identities as part of their normal calculus program. They might just do the trig modelling internal, and identities are, they creep up a lot in scholarship, particularly in differentiation problems, integration problems. Okay, so this one here we don't need too much knowledge of complex numbers. We just need to know how to deal with this. Z equals cosine theta plus I sine theta, or cis theta. What that tells you is that the modulus of z is equal to 1. So the thing that we're actually proving here only works if the modulus of z equals 1. If it was any other modulus, so r cis theta, then this proof wouldn't work. Okay, so what we can do is we can just substitute that z complex number into the problem. And we set out a proof like this. Left-hand side equals 1 over 1 minus, and then we've got to be careful of our integers here. We've got cos theta plus I sine theta subbed in, multiplied by cosine of theta. This is a complex number, and it's also 1 divided by a complex number, so it's not in its standard format at the moment. We do a little bit of tidying up first though. The denominator there can be simplified to 1 minus cosine squared, and then minus I times sine theta cosine theta. And then you might spot that this trig identity appears quite often in questions. 1 minus cosine squared is the same as sine squared. So we've got 1 over sine squared theta minus I times sine theta cos theta. Now, because we're simplifying this down to quite a simple expression on the right hand side, 1 plus I cotan, I'm going to try and simplify this a little bit more. So I notice in the denominator there's a factor of sine theta in both terms. So if I can factor that out, sine theta there multiplied by sine theta minus I times cosine theta, this kind of sets up nicely for using the conjugate. Remember that, as I said, this complex number is not in a standard format, but if we multiply it by the conjugate of the denominator, we don't need to worry about that sine theta factor, that can stay there, but if we just times by sine theta plus I cos theta on the top and the bottom, as I tell my students, we're timesing by 1 here, so we're not changing the expression, we're just making it look different. Makes it look horrendous, but actually the denominator will simplify as it always does. Okay, numerator is just 1 times the stuff on the right, so sine theta plus I times cos theta. And the denominator, well, there was a factor of sine theta. And then if we look at these two terms here, this term multiplied by that term, that's a difference of 2 squares, which means you get the first thing squared, sine squared theta, and you get the last thing squared. Minus I cos theta times I cos theta is cosine squared times negative I times I. There's an I squared in there, and an I squared is negative 1. So if we times that there, I by I, we get I squared, which is negative 1. There's also the other minus, so that's plus 1, and then it's cos times cos. So we're getting plus cosine squared theta, and lo and behold, that trig identity there, rears its head. That there is equal to 1 always, no matter what theta is. And so if we simplify this down, we've got sine theta plus I cos theta all divided by sine of theta. The green part was 1, and we've got our proof, because sine theta over sine theta is 1, and I times cos over sine, which is cotan. That was what we were trying to prove. Happy days. Now, the second question here, we could substitute in cosine plus I sine theta, or we could substitute in x plus iy. And the marking schedule does do that, but to be honest, I prefer to look at these problems geometrically when there's arguments involved, because arguments are angles. So if we just sketch an argon diagram and put in the x-axis as our real axis, the y-axis is our imaginary axis. The first thing we were told for this proof, and this is the second part of if z equals cos theta plus I sine theta, as I was saying at the start, the modulus of z has to be 1 here. So what does that mean in the context of this? Well, if we put a complex number somewhere in the first quadrant, the question did tell us that it was in the first quadrant, the argument was between 0 and pi over 2, then if we put z there, this length here, helps if I actually draw it correctly, that length there equals 1 because it has a modulus of 1, the distance to the origin. And then this angle here is the theta. Now, on the left-hand side of this proof, we've got z plus 1. So the question is, well, where is z plus 1? If you take a complex number z and you add 1 to it, you're just adding 1 to the real part. And when we add to the real part in the argon diagram, we move to the right by 1. So that length is 1, and that complex number there would be z plus 1. Now the question is, what's the argument of that complex number? Well, we would just draw a dashed line from here to the origin, and that angle there would be the argument of z plus 1. Let's just call it alpha. So let's say that that thing there, argument of z plus 1, is equal to alpha. And we just need to prove that 2 lots of that angle alpha is equal to the argument of z, which is theta. Okay, how do we do that? Very easy using geometry. That angle must be alpha because we have some parallel lines here. Alternate angles on parallel lines are equal. And we have an isosceles triangle there, which means that this angle here must be alpha. And we're done. So by using angle geometry rules, actually, angle geometry rules sounds pretty lame, let's say geometric reasoning. And we probably should put those reasons, alt angles, parallel lines are equal. And what was the other one I used? Base angles, isos triangle equal, we get theta equals 2 alpha. So we've proven the result. Okie dokie. Now for this question, I said from the outset of this video that you need to know your definitions of your conic sections, in particular a parabola. So if you Google a parabola on Wikipedia, it says that it is a curve that fits several superficially different mathematical descriptions, which can all be proved to define exactly the same curves. One description of a parabola involves a point, the focus, and a line, the directrix. The parabola is the locus of points in that plane that are equidistant from the directrix and the focus. So this question's actually specifying the definition of a parabola. I'm just going to use the picture straight from Wikipedia here, and then we'll just rotate it around. If you search up Wikipedia, you'll see that they have a parabola that's upright. They have a point there called the focus, and they have a line that's equidistant. So what I mean by that is that line there, the distance from the parabola to the focus is equal to that distance there. It's close enough. We've got this line going across called a directrix. And anywhere on the parabola, and you can prove this quite easily. For example, this point, that line there is equal to that line there. It doesn't look like it because my curve is dodgy. It's not, I haven't drawn a parabola. I've probably drawn half of a almost a half an ellipse, but okay, there we go. That's a locus definition. So this question here says, consider the locus of points that are the same distance from P, a point, as they are from the line, that line there. So this would be the focus, and the line would be the directrix. So if we were to quickly sketch that, and that would be our answer. So we've got a coordinate system in here. This parabola is tilted. Part of the reason probably why the examiner said do not find the equation of it, because it's tilted. If we put in the line y equals a half x, that's actually the axis of symmetry. And then the line y equals minus 2x is perpendicular to that axis of symmetry. Another feature. And the focus is some point P. The P is actually able to move because 2P depends on what the value of P is. So let's just put it there. There would be the focus. Halfway between those points, halfway between the origin and that point would be the vertex. And then we would have a parabola that kind of opens up like that. So at any point on the parabola, the distance to the focus is equal to the distance to the directrix. I'm just going to show you a GeoGebra diagram that I made for this to convince you, because my drawing might not. What I did is I put in the equations of the lines that were given in the question. So you've got the directrix minus 2x and the axis of symmetry half x. Some point that's on it. Now this point can move, but it's stuck on that line. Then I found the midpoint of it. The parabola here, see, it's got its equation, and it's an absolute mess, and it depends on what P is. So if I move P, then the equation changes. But that to make that parabola in green, I actually used one of the functions up here on GeoGebra, which says parabola, and you have to specify the focus and specify the directrix which are in place, and we've talked about them being P and then that line y equals minus 2x. So I cheated, I used a function. Point C is any point that's on the parabola, and then I show you that those distances there, those distances eventually, there we go, they are equal. And if I move point C to somewhere else on the parabola, those distances are different, but they're also equal. I should have mentioned from the outset that when we talk about a distance to a line, we're talking about a perpendicular distance. So that angle there, 90 degrees. And then lastly, if you can see down on the bottom left, I have equation 1, and it's written in a different format. It looks nicer than the first equation, but it's actually the same equation. And the way I found it was to use coordinate geometry, even though the question didn't said you didn't have to use it. You could. Okay, so to do that, you would have gone the distance from P. What is the distance from P? Well, if we make this coordinate here xy, then the distance from xy to P, we could just use Pythagoras to find that. We would be going square root difference between the x values, which is x minus 2p all squared, and the difference between the y values, which is y minus p all squared. And that distance is equal to another distance, the distance from xy to the line y equals minus 2x. But this equate, or to find the equation, or expression that represents that, you actually need a formula that's outside the NCA syllabus. If you're interested, go and look up on Google the distance from a point to a line. I think Cambridge students learn about it when they do vectors. There is an equation that will calculate that, and then you will have your locus equation as a parabola. It's a tilted parabola though, so it's not an easy equation. Alrighty, this second part here, we actually do need to find the equation of the locus, but fortunately it is a nice one. Just before we get started on this, I've made another GeoGebra diagram to help us understand it. So you've got a point P which is moving along the line, and a point Q that's moving along another line. Notice the difference in the question here. It says point Q. We're actually not talking about the distance to a line anymore, but the distance to a point. And the ratio's changed. It's now 3 times as far. So I asked my students in class to sort of come up with a position that kind of works for this. So if I was to draw a line between Q and P and divide it into 4 bits, this point here would have to be on the locus, because it's 3 times as far from P as it is from Q. But then maybe so would this point, because this distance here and that distance there would be a 3-to-1 ratio. So it turns out there's an infinite number of points that satisfy it. And if you've seen questions like this before, you'll know that it's actually a circle. But if you weren't in the know there and didn't know about the circle of Apollonius, either Google it and learn about it, or just think about what the question's actually asking us. It's telling us in the question that P, which, be careful here because P is actually the y value of the coordinate P, P and Q are changing, and when they change, the region, the locus, is increasing. And it asks us about the area of the locus. And so you think about all of the sort of shapes that you know how to find the area of. Well, the first question we did was a parabola, and what is the area of a parabola? Well, it's not even a closed region, so that doesn't make sense. So for this question, for it to be a closed region, it's likely to be a circle or an ellipse, just so that we can find the area of it. Okay, so let's just talk through briefly what I've done here. Notice that up the top left that x is actually the coordinate P, and it's defined parametrically. So the y value starts at 3, but it's 3 plus 3t, which means that the y value is increasing 3 centimeters per second, or 3 units per second. And then the x value of it is just 2 lots of that, because the coordinate was 2p. And at the moment I've specified time equals 0, and so P and Q are exactly where they are in the diagram, but you're to realise that time changes and therefore P and Q move. So if I change it there, ignore the pink dots for now, P and Q, they move. Okay, but we are actually focusing on what happens when time is 0. Similarly, I've done the coordinate of Q parametrically. It starts at -4 and it decreases by 2 every second. That's the x value, and then the y value is just -2 lots of that. It's on the curve, it's on the line y equals -2x. Now, you can see these circles here represent distance. So if you look at the coordinate A, for example, A is some distance away from Q. It's actually 3.83 away from Q, and it's a total of 3 times 3.83 away, because I've set these circles up so that one has a radius of r and the other has a radius of 3r. So A and B there are points that are on the locus of Z at this particular point in time. And if I just move these circles and make them smaller and bigger, then that there in pink is the locus of Z currently. The locus of points, I keep saying Z, but we don't have to do complex numbers in this problem. The locus of points that are 3 times as far from P as they are from Q. Now, it's a circle, so to find the area of it, we would just need to find its radius. Now, also think about the fact that when these points have moved, the locus is now a bigger circle. So the circle is changing its area, and so therefore we need to find out how the radius depends on time. Okay, so one of the ways you can do this is parametrically, but it turns out it is a bit messy. So I'm just going to do it without parametric equations. So first up, we've got some point here, xy, where the distance to Q multiplied by 3 would equal the distance to P. So if this was r, like it was in the diagram, this would be 3r. Okay, and now we're just talking about distances to points, not distances to lines. So we can use Pythagoras. The distance between xy and the point Q is x minus the x value of Q, which we are told is equal to Q. That's helpful, but you've got to be careful for the other one. And we've got y minus negative 2Q all squared. Be careful of integers there. Now, the distance to P, 3 times this, got to put the 3 on the right side of the equation, x minus the x value of P, which from the top is 2P, it's switched around, and then y minus P, all squared. So that equation there, we have to realize it's a circle, and it doesn't really look like one at the moment, but if we expand out the stuff, we're going to notice pretty quickly it's a circle. Let's just move that down there, and square both sides. If we square both sides, we get 9. This stuff here will expand, the square root will disappear, but we're going to get 4 times Q times Y. And 4 times Q times itself. I'm being very careful of how I say the number 4 with the letter Q. On the right hand side, we're getting x squared minus 4p x plus 4p squared. And we've got y squared minus 2py plus p squared. And no doubt I will make an error at some point in this video because it's an absolute mess. Okay, what you need to realize there is that the x squared term will make 8x squared if we rearrange it, and the y squared term will also be 8y squared. And so when you have an equation where the same number of x squared and y squared exist, it will be a circle. And remember, we only want to find the radius of the circle. We don't care about where it's positioned. The area of a circle is defined as pi r squared. We just need to know the radius. So we're going to do a bit of rearranging. We've got 8x squared. That's the first term there. We've got minus 18qx on the left, and then on the right hand side we've got minus px, which will go to be plus 4px if I put it to the left. So that's all the x terms dealt with. And then we've got, I'm going to leave the q squared term because let's just deal with the x's and y's first. So we've got 9y squared, but the y squared on the right goes to the left, it's 8y squared. We've got 9 times 4q, oops, I made the mistake there. Now you'll know what I was talking about earlier. 36qy, on the left. On the right, we've got minus 2py. So plus 2py. They're all the terms with x's and y's. And the other stuff I'll leave on the right-hand side. 4p squared. No, it's not 4p squared. Apologies, it's 5p squared. It's those two terms there. And how many q squareds have we got on the left? We've got 5q squared inside the brackets times 9, 45, but minus 45 if we put it to the other side. Okay, and that's all of the terms moved around. If I divide everything by 8, just to make it look a little bit nicer, 4p minus 18q, all divided by 8, lots of x, y squared. Do the same thing with the 36qy and the 2py. 36q plus 2p all over 8 times y. And on the right hand side, I've got to make sure I also divide that by 8. Okay, so it's a circle. And whilst I don't need to find the centre of it, I do need to complete the square on it, because that will now enable me to get the radius. Completing the square means I'm going to go x plus something all squared minus that something squared. Then I'm going to have y plus something all squared minus that something squared. And on the right hand side I'm going to get r squared. And because we just want the r squared term, I can just focus on that. R squared is the thing that's already on the right hand side plus the square squared and the triangle squared. Now to get that, remember to get these terms here, that's half of this term, and this one is half of that term. So I'm going to add, because it's going to go onto the other side of the equation, 4p minus 18q over 16 all squared, 16 because it's half and it was 8, so now it's over 16, plus 36q plus 2p over 16 all squared. Now that is the radius squared, and it turns out it simplifies quite nicely. I must say at this point I cheated and used Wolfram Alpha. But if you expand all this stuff out, a lot of terms cancel. You end up with the radius squared is equal to 45 over 64 multiplied by p squared plus q squared. And remember that the thing we're trying to find is the area of this region, and it's in terms of p and q here. So the area of our region is going to be pi times r squared, 45 pi over 64 times p squared plus q squared. At this point you could make p and q in terms of time, like I did on the outset in the GeoGebra video, in the GeoGebra diagram, and define p and q parametrically. Or you could have done that right from the outset and put time into that first equation in red, but you don't need to do that if you know implicit differentiation. To differentiate this with respect to time, to find the rate that the area is changing with respect to time, we diff this equation with respect to time. 45 pi over 64 just sits there. To diff p squared with respect to time, we differentiate it with respect to p, and then we put dp dt afterwards. And similarly with the q squared one, we go 2q, and then, oopsies, 2q multiplied by dq over dt, the rate that q changes with respect to time. Now that equation is all good for substituting in, because the original problem told us that at the position when p is equal to, I've got to be careful again here, little p was the y value. So when little p is equal to 3 and little q is equal to minus 4. When little p equals 3 and little q equals minus 4. Now we're also told the rates dp dt and dq dt, dp dt in the question, p P was increasing at a rate of 3 and Q is decreasing at a rate of 2. So dp dt equals 3 and dq dt equals minus 2. And then we substitute those four numbers into this expression. dA dt 45 pi over 64, 2 lots of 3 times 3, plus 2 lots of minus 4 times minus 2. And if you work that all out, it simplifies to 765 pi over 32. Now, if I had gone back to my GeoGebra diagram and I'd looked at the exact time that we're talking about, which was time equals 0, and then if I had slightly changed time to, like, I don't know, 0.001, therefore P and Q slightly changed, and therefore the coordinates P and Q slightly moved, and then I calculate the new area, the difference in the areas from the original area of the circle to the area some smidgen of time later would be approximately equal to this rate. So I could check that on GeoGebra to see that I've got the right quantity, but of course in an exam you can't do that. So yeah, like I said, it's a really, really difficult problem. There's a lot going on there, but it is one of those questions that tests out the top students. Hope you found the video useful as always. All the best of your studies.